Welcome to Math TV with Professor V. In this video, we're going to look at determinants, how to find the determinant of a matrix, and how to solve systems of linear equations using Cramer's rule. So what is a determinant, you might be wondering? Well, definition tells us that the determinant is just a number that's associated with a square matrix. So first thing, remember your matrix has to be a square matrix, same number of rows as columns. And the determinant is just some number that's associated with it. It's a scalar quantity. And the way we denote the determinant is one of two ways. You either write the name of the matrix inside two vertical lines. Kind of looks like absolute value bars, but it's not. Or you could just write DETA. And that indicates that you're taking or you're finding the determinant of your matrix A. So we're going to look at the most basic case first, how to find the determinant of a 2 by 2 matrix. So if we have the following 2 by 2 matrix A with entries labeled as follows. So you see how in the upper left we have A11. That means that's the entry in the first row, first column. A12 means first row, second column. A21, second row, first column, etc. Second row, second column. So those represent whatever the entries are. If I'm finding the determinant of A, it's equal to the product along this diagonal here, A11 times A22, minus, then you subtract the product of the other diagonal, A21 times A12. All right, so let's give it a go. Example 1 says, find the determinant of the following matrix. Notice here I have brackets outside my matrix, so this just is a regular old matrix hanging out. As soon as I switch those brackets to vertical lines like this, now that indicates I'm finding the determinant, okay? So just be careful with your notation. I'm going to take the product along this diagonal here, so -6 times 2, and then I'm going to subtract the product along the other diagonal, which is 4 times 3. And then we're left with -12 minus 12, which is -24. All right, so the determinant of that matrix is equal to -24. The significance of the determinant and how we use it will be studied later on. Right now, let's just focus on computing it, okay? So 2 by 2 matrices, not hard to find their determinants. What about when you have a 3 by 3 matrix? Well, we need a little extra terminology before we can talk about how to find those determinants. Say we have matrix A. Remember, it needs to be a square matrix, and it's of order n greater than 1, and we're labeling all the entries like I labeled that 2 by 2 matrix above. So A sub ij, where I represents the row, j represents the column. We say that the minor m sub ij of the element A sub ij, so each element in a matrix has a corresponding minor, and that minor is the determinant of the matrix of order n minus 1 obtained by deleting row I and column j. Okay, then the cofactor A sub ij, capital A, of the element aij is nothing more than just the minor, right, for that element, times -1 raised to the I plus j. So don't worry if these definitions are a little over your head. If it's the first time you've seen it, we're going to work through an example right now to help break things down. All right. So let's find M11, M23, A11, and A23 in the following matrix. So M11, the minor corresponds to the element A11, and it's equal to the determinant that results when I delete row 1, column 1. So you look at whatever the subscripts are here, you're gonna delete from this 3 by 3 matrix that row and delete that column. So if I delete row 1 and column 1, I'm left with the following 2 by 2 matrix. 1, -3, -2, 2. Do you see how that works? That's why in the definition, it noted that the determinant of the resulting matrix is going to be order n-1. So if you start with a 3 by 3 and then you're finding the minor of some element, then you would take the determinant of a 2 by 2. It always will go down. Okay, and then this, we know how to do 2 by 2 determinants, don't we? So 1 times 2, that's just going to be 2, minus, and then this is -3 times -2, which is +6. So this is -4. Okay, not too bad. Now let's find M23. So M23 is going to come from computing the determinant when you delete row 2, column 3. It's always row, then column, row, then column. So let's see what's left over. We've got -6, 4, 5, -2. And now let's compute this determinant. So we have here 12, +12, minus 4 times 5, which is 20. And this gives us -8. Lovely. Lovely, lovely. So that part's done. Now we're going to find cofactors. A11, look at the definition. Capital A11 is going to be -1 raised to the I plus j. I and j are both 1. So raise it to the -1 plus 1 times mij times m11. All right, let's see. This is -1 squared. Don't we have m11? Didn't we just figure it out? Oh, why, yes, we did. It's -4. So this is +1 times -4, which is -4. All right, and then similarly for M23, we can find A23, that cofactor. So it's -1 raised to the 2 plus 3 times M23, which is going to be -1 raised to the 5th. What's M23? Oh, we have it here. It's -8. Lovely. So then that's -1 times -8, which is 8. Okay, not too bad, right? Good. So now that we know what cofactors are, we can talk about how to find the determinant of a 3 by 3 matrix. So the determinant of a 3 by 3 matrix is as follows. You take the entry A11, look at that, and then you multiply by its cofactor, plus then you take the entry A12, you multiply by its cofactor, plus you take the entry A13, and you multiply by its cofactor. And actually, you can use any row or any column to calculate the determinant. You don't necessarily have to go across row 1. Alternatively, you can go down column 1, across column 3, row 3, whatever you want. The best plan of attack is to choose a row or a column that contains the most zeros and ones when you're choosing which row or column to expand upon. That's what we call it when you're finding the determinant. And I just want you to notice something, because remember the cofactor involves that -1 raised to the I plus j. So if we look at this in more detail, this is basically A11. And then remember that cofactor would be -1 raised to the 1 plus 1, and then times M11, plus A12, little a12. And then capital A12 would be -1 raised to the 1 plus 2, which is 3, times the minor M12, plus lowercase a13, and then capital A13, the cofactor would be -1 raised to the 1 plus 3, which is 4, times M13. And what's interesting is notice this second term will remain negative because you have -1 cubed, but the others will not. And that pattern continues because anytime a term has subscripts that sum up to an odd number, then you'll have that extra negative, right, when you're finding the determinant. So you can just keep in mind the signs will alternate from that -1 to the I plus j. I plus j is positive, will give you -1 to a positive number, negative, positive, negative, positive. It just alternates throughout the matrix. Okay, so let's go ahead, let's practice taking some determinants, and then I do have another method to show you, so don't worry. Find the determinant of A. So we have the matrix 5, -2, 1, 4, 7, 0, -3, 4, -1. Now, I'm going to choose to expand along column 3 here because that column has the most zeros and ones. So it's really going to make my life a lot easier in the computation. Okay, so let's give it a go. The determinant of A, I'll write it this way, is equal to, so I'm going to start here, take 1, and then I'm not going to write out -1 to the 1 plus 3. I'm just going to use the fact that the signs alternate like I showed you here. So I'm going to leave this first term positive, multiply by the minor. The next one negative, multiply by the minor, and then positive. So watch. I have 1 times, now get rid of this row, this column, multiply by the determinant of the 2 by 2 that's left over. 4, 7, -3, 4. Good? Excellent. Now I'm going down column 3. I did that one already. Boop. I switched the sign here. -0 times the determinant that results when I delete the column and row that 0 is in. So that would be 5, -2, -3, 4. I didn't even have to write that out because 0 times anything is just going to be 0 in this case. So that's why we like picking the rows and columns that have the most zeros. Also notice I switched the sign there. It didn't affect this determinant because that was a 0 anyways, but the signs will alternate. And then I have plus -1. And then now I'm going to multiply by the determinant from deleting that row and column that contain -1, that entry. And we have the determinant of 5, -2, 4, 7. All right. Good. So let's see here. This is just 1 times 16 minus -21. So that's 16 plus 21 minus 0. This guy's just gone. And then minus 1 times, let's see, this is 35 plus 8, yes? 35 plus 8. Okay. And so 1 times 16 plus 21, that's 37. Minus 35 plus 8, that's 43. So we're left with a -6. So the value of this determinant is -6. And no matter which row or column you choose to expand upon, you'll get the same answer. Okay, it's just some computations may be easier, less of a chance of you making a mistake. Now let me show you another method that a lot of students like. It's very similar to how we take the determinant of a 2 by 2 matrix. And it's a little less thinking, so you might like it. So you write out the original matrix whose determinant you're trying to take. So 5, -2, 1, 4, 7, 0, -3, 4, -1. Good? Okay, usually I'll separate with some dashed lines, and then you rewrite the first 2 columns in columns 4 and 5 now, okay? So I'm gonna write 5, 4, -3. Am I good? Am I good? Yes, I am. And then the next column is -2, 7, 4, okay? And so now you have a matrix, or you're taking the determinant of something with 3 rows and 5 columns. So watch this. Remember how we did the 2 by 2 matrix? Its determinant with all the diagonal products? Same idea here. You're going to take the product of this diagonal plus the product of this diagonal plus the product of this diagonal. So we've got 3 of them. So let's see. We have 5 times 7 times -1 plus -2 times 0 times -3 plus 1 times 4 times 4. You take those entries and then you subtract the product of diagonals going the other way, like we did in the 2 by 2. So subtract the product of that diagonal, and that diagonal. So subtract -3 times 7 times 1 plus 4 times 0 times 5 plus, oh, we gotta scoot over, scoot, plus, last one is -1 times 4 times -2. Okay? All right, and then let's see what we have. So 5 times 7 times -1, that's -35 plus 0 plus 16. And then this negative is going to distribute, right? Yes, of course. So that's going to be plus 21 minus 0 minus 8. And 16 and 21, that's 37. 37 minus 35, that's 2 minus 8, -6. Same result as other method. Which one do you think was easier? I think this alternate method, right? You can just kind of zone out and do those diagonal products. Anyways, when I was in school, they didn't show that to me. I learned that later in life. So use both methods, depending on whatever preference you have. Now, properties of determinants. We can also use some of these properties to make computing them easier. Or they're just good facts to keep in mind. So the value of a determinant will change signs if any 2 rows or any 2 columns are interchanged, okay? So if you swap 2 rows in a matrix, the determinant of the new matrix will have the opposite sign of the original. And then if all of the entries in any row or any column are 0, then the value of the determinant is 0. If any 2 rows or columns of a determinant have corresponding entries that are equal, so you have like a duplicate row or column, then the value of the determinant is 0. If any row or any column of a determinant is multiplied by a non-zero number, k, some constant, then the value of the determinant is also changed by a factor of k. And then this is useful here. This is the one we're going to use. If the entries of any row or any column of a determinant are multiplied by a non-zero number k, and then the result is added to the corresponding entries of another row or column, the value of the determinant remains unchanged. So if you know basic row operations, you can perform this row operation and the value of the determinant will remain the same. So I'll show you how to do that in a minute. And then we have the following definition again for a matrix and how to find its determinant, but this time we're talking about the determinant of a matrix A that has order n, not just order 3. So the definition can be expanded upon for any square matrix, 4 by 4, 5 by 5, etc. And you would just repeat the process. It can be tedious, and most of the time you don't need to worry about doing a determinant for a matrix larger than a 3 by 3. But just so you know, you would repeat the process, expand upon any row or column, and then when you're multiplying by the cofactors, then you would have to compute another determinant for a 3 by 3 in order to keep going if you start with a 4 by 4. For example. Okay, so let's look at an example here where we're going to find a determinant, and I'm going to use one of the properties of the determinants to make it maybe a little more simple to compute. Okay, notice I don't have any zeros in any rows or columns at the moment, so none of them are looking too appealing to me. So what I want to do is actually make a 0 in the matrix. Oh yeah. How am I going to do that? Say I want to make this 3 a 0. Well, we have a limited set of row operations that we're allowed to perform with matrices. And one of them is you can multiply any row or column by some constant and then add it to another row or column. So what I'm going to do is take row 2 and multiply by -3. So -3 times row 2 is going to give me -3, -12, -6, right? And then I'm going to add that to row 1, 3, -9, 4. And I'm going to be left with 0, -21, -2. And this is my new row 1. If you'll remember your row operations, whichever row you add to, that's the one that gets replaced, okay? If you mess it up, then the sign is going to come out wrong. So be careful. So now, instead of computing the determinant of the original matrix A, I'm actually going to compute the determinant of the following matrix: 0, -21, -2, 1, 4, 2, and then this entry is 8, -3, 1. And you can pick any row or column. I say let's use the first column because there's a 0 and a 1. I like it, okay? So we're going to find the determinant of 0, -21, -2, 1, 4, 2, 8, -3, 1. All right, so you take that first entry, 0, and then I'm not even going to worry about multiplying by anything. Then the signs alternate, right? So minus 1 times the determinant that results when I eliminate that row and column. So times the determinant of -21, -2, -3, 1. Okay. Things are looking good. And then last entry here, plus 8 times the determinant that results when I delete that row and column. So I have -21, -2, 4, 2. All right, so what do we have here? We have 0 minus, this product is -21 minus 6 plus 8 times, this is -42 plus 8. Yes, -42 plus 8. So what do we have now? That's -27 times another negative, +27, plus 8 times -42 plus 8 is -34. Okay, so we've got 27 minus 272, which is -245. Okay, so that's just one option. You didn't have to do that. You could have worked with the original matrix when you found the determinant. Or let's try that alternate method that I showed you, where you add 2 columns and just take products along the diagonal. Let's see how we feel about that. And I'm not going to mess with the original matrix and do any row operations. So I'm going to find the determinant of, remember, you rewrite everything you have first. So 3, -9, 4, 1, 4, 2, 8, -3, 1. And then rewrite the first 2 columns, 3, 1, 8, -9, 4, -3. And then now we just take the products along a bunch of diagonals. So we're going to have this product times this product times that product plus the other product plus the other product. So we have 3 times 4 times 1, that's 12, plus -9 times 2 times 8, that's -18 times 8, plus 4 times 1 times -3, that's -12. And then I subtract the sum of all of these products. 1, 2, 3. So 8 times 4 times 4, 8 times 16, plus negative 3 times 2 times 3, that's going to be negative 18. 1 times negative 9, minus 9. Okay, and we've got here, notice these 12s cancel, right? So I just have negative 18 times 8, that's negative 144. Then let's distribute this negative. That'll be negative 128 plus 18 plus 9. And lo and behold, we get negative 245. Oh my goodness, wasn't this method so much easier? Even after we tried to make the 0 in the matrix. So it would be nicer. Anyways, keep this alternate method up your sleeve. It's rather useful. Now, one useful application for determinants is that they allow us to solve systems of equations using Cramer's rule. So say you have a system of equations and D is the coefficient matrix. So it's the matrix made up of all of the coefficients from the variables when they're listed in standard form, like such. D sub x1 is the matrix obtained from D by replacing the coefficients of x1, or the first variable in that first column, by the constant numbers, so by these numbers over here. D sub x2 is the matrix obtained from D by replacing the coefficients of x2, or the second variable, by the constant numbers, by the ones over here. Okay, all the way up to D sub xn. Then you can solve for each of the variables x1 by taking the determinant of D sub x1 and dividing by the determinant of D, and you can do that for all of the corresponding variables. So this is a clean way to solve for a system of equations without having to, diagonalize, use Gaussian elimination, or mess around too much. Now just notice though, because you're dividing by the determinant of D, right? When you're solving each time. So if the determinant of D is equal to 0, Cramer's rule will not help you solve the system entirely, because that means the system is one of two things. It's either a dependent system, which would have infinitely many solutions, or it's inconsistent. And we'll talk about a little more detail if that were to happen at the end of the video, okay? So let's see how this works. We're gonna use Cramer's rule to solve the system. And this problem asks us right here in part A just to solve for x, okay? Oh, how nice. When I was working this through, I did all of them. So first you start off by writing out D, which is the matrix of all of the coefficients, okay? So here we go. Have that ready. So D, if you just take the coefficients of the variables, it's going to be 1, 3, negative 1, 3, negative 1, 2, 2, negative 1, 1. This is D. And then now we need the determinant of D. No problem. So the determinant of D, pick any row or column to expand upon, or you can do the alternate method. I'm just going to do it the old school way that they taught me when I was a wee one. I'll just go along row 1. So I'll take 1 times, I'm just going to do it visually, you guys, because I think by now you got the pattern. Negative 1, 2, negative 1, 1. Then you alternate signs, so now it's minus 3 times, if I delete this column, this row, what's left over? 3, 2, 2, 1. Minus 1, don't change the sign. Delete this row, delete this column. What's left? 3, negative 1, 2, negative 1. Yes? Good. So this is 1 times negative 1 plus 2, yeah. Minus 3 times 3 minus 4, minus 1 times negative 3 plus 2. Remember, all these determinants are just difference of the diagonal products. And then we're left with 1 times, that's just 1, minus 3 times negative 1, minus 1 times negative 1. So that's 1 plus 3 plus 1, which is 5. Ooh, okay. Now that I have that, I can go ahead and try to solve for x. So first, I need to figure out what d sub x is. And d sub x comes from taking the matrix D, the coefficient matrix. So I'm just going to copy it below. Copy, paste. Fantastic. But since I'm solving for x, you delete the column of the coefficients of x, right? That's where all the x's were. And I'm going to replace it with what the constants are. -3, 1, -1. Let me switch colors so you can see what happened. -3, 1, -1. Got it? Since we're solving for x, I'm going to replace that first column, the x column, with what everything's equal to. Now we find the determinant of this guy. So the determinant is equal to, let's just go along first row again. Try the alternate method on your own if you want while I'm doing this. If you like that way better, go for it. -3 times, let's see what's left over. That's gone, that's gone. It's going to be -1, 2, -1, 1. Then switch the sign for this next entry here. So -3 times, if I get rid of that row, that column, I have left 1, 2, -1, 1. Yes, yes, yes. Then don't change the sign on the last one. So that'll stay -1 times, get rid of that row and column. I have 1, -1, -1, -1. All right, and so get out of here. We have -3 times. That's -1 plus 2 minus 3 times, this is 1 plus 2 minus 1 times -1, minus 1. So we've got -3 times 1. Minus 3 times, this is 3, so minus 9. Minus 1 times -2, so plus 2. That's -12 plus 2, which is -10. So that tells me x, which is equal to determinant of d sub x divided by determinant of d, is going to be -10 divided by 5, which is -2. Oh, how lovely, right? Okay, so if you wanted to solve for y or z, you could continue. Let's do it. It didn't ask us to, but I feel like being an overachiever. So for y, I need first the matrix where, remember you take D. Where did D go? Let's go back to the original right here. Take D. Since we're solving for y this time, I'm gonna get rid of the column that contains the coefficients of y. So this is D. I want D sub y. So this goes away, okay? And then now I'm going to replace that with the constants. Remember here what everything was equal to, -3, 1, -1. Yes, -3, 1, -1 replaces the column where the coefficients of y were. So we've got -3, 1, -1. Okay, looks good. So now let's take the determinant. I'm just gonna stick with row 1. Do what you want, even do the alternate method. Give that a go. So determinant of d sub y is gonna be 1. So this entry, and then now delete this row, this column, multiply by the determinant that remains. 1, 2, negative 1, 1. Now next entry, you're going to switch the sign, right? So it's going to be plus 3 times, get rid of this row, get rid of this column. We have the determinant of 3, 2, 2, 1. And then minus 1, leave that alone, times the determinant of 3, 1, 2, negative 1. Good. So we've got here now 1 times, this is 1 plus 2, plus 3 times 3 minus 4, minus 1 times negative 3 minus 2. All right, so 1 times 3 plus 3 times negative 1, that's negative 3, minus 1 times negative 5, so plus 5. And the 3's cancel out, so I'm just left with 5. That means we know what y is, don't we? Y is determinant of d sub y over determinant of d, which is 5 over 5, which is 1. So we've got x and y. Technically, we could just substitute in x and y into one of the original equations and solve for z. But just check with your professor if they want you to only use Cramer's rule to solve the whole system, if you have an exam or something like this. I'm just going to still use Cramer's rule to solve for z. Let's use the alternate method, huh? Why not? So d sub z, again, I'm going to go back to the coefficient matrix, 1, 3, 2, 3, negative 1, negative 1, and then I'm going to replace the third column with negative 3, 1, negative 1, right? Remember, that's what it was. I'm not going to keep scrolling up and down. You can reference your notes from earlier. So let's find the determinant, and I will use the alternate method, so I'll add on the first two columns again. 1, 3, 2, 3, negative 1, negative 1, negative 3, 1, negative 1, and then rewrite 1, 3, 2, and 3, negative 1, negative 1. Beautiful. Let's see. So we've got, I like to draw them in first before I get going. 1, 2, 3, there we go. So 1 times negative 1 times negative 1, that's 1. 3 times 1 times 2, 6. Negative 3 times negative 1, positive 9. Then I subtract this product, this product, this product. 2 times negative 1 times negative 3, that's 6. Negative 1 times 1 times 1, negative 1. Negative 1 times 3, negative 9. So 1 plus 6 plus 9, that's 16. Minus, what's this? Negative 3 minus 1, negative 4. So that's 20. This is a million times easier. I wish they had taught me this when I was in school. Okay, so then z equals determinant d sub z divided by determinant of d, 20 over 5, which equals 4. Okay? And then you're not going to be some sloppy student. You're going to write your final answer, if you're asked to solve the system, as a beautiful ordered triple in a solution set. Yes? You shouldn't leave the values scattered about your paper. Make your instructor go on a scavenger hunt trying to find your solution. Right there. Bam. And I did promise to tell you what it meant when the determinant was 0, right? Okay, so let's talk about it because it can happen sometimes. Let me add a little page in here and I'll just summarize kind of what to do when the determinant's 0. So if the determinant of that coefficient matrix is equal to 0 and at least one of the determinants dx or determinant of dy or determinant of dz, assuming it's only 3 by 3, is not 0, then the system is inconsistent. When it's inconsistent, remember, that means that there's no solution. And so you could write out your final answer as the empty set. So that denotes the empty set, or you can write an actual empty set. I like that one. It's got good flair to it. Okay, other scenario, if the determinant of that coefficient matrix and all of the other determinants, so dx, dy, dz, whatever variables you have, if they are all 0, all of them, then that means the system is consistent, okay? It will have a solution. It's just that it's dependent. So that means it has infinitely many solutions. Okay, so how would you solve? It depends, right? It's dependent and it depends. So you need to solve either using row reduction techniques or algebraic methods, because there's more specific ways to write out the solution set, right? Depending on what kind of dependent system you have. When you have 3 equations, 3 variables, things can get a little more involved. So Cramer's rule won't help you figure out the final solution. It can if the system's inconsistent, because you can tell one of these determinants is non-zero, so empty set, done. But in this case, when you have a dependent system, to finish the problem, it must be solved with row reduction techniques or just algebra, elimination, substitution. Okay, good. Hope you found this video helpful. Give it a thumbs up if you did. Share it with whoever you think would find it helpful. And stay tuned. We have more stuff on matrices coming. It's been a hot topic requested lately.